Hello, my name is Jeff Hazboun, and I'm a NANOGrav postdoc at the University of Washington, Bothell. And I'm going to be talking about some advanced noise modeling work that we have been doing in the detection working group, specifically on the 12 and a half year data set. Although this is an extension of work that was started by Joe Simon and Steve Taylor on the 11-year analysis. Joe is working on the methods paper for this, and we're hard at work working on looking at individual noise models for all of our pulsars. And I'll say a little bit more about what that means, but this is a pretty personnel intensive activity. And down below here is a list of the folks who are currently involved and who have adopted pulsars. And I will have an advertisement at the end if you're interested in working on this project. So our standard noise model, at least from the gravitational wave analysis side of things, involves 3 white noise parameters. And if you want more details about these, the NANOGrav glossary is a good place to look. But there's E-core, E-quad, and E-fac. And we set those constant in the analysis, but when we're looking at individual noise analyses for the pulsars, we let them vary, and then we figure out what the best values are for them for the full gravitational wave analysis. We also throw in a power law red noise model. So this is power spectral density and modeled in the frequency domain. We use a Gaussian process to do that. And we're just looking for these time correlated errors in the times of arrival that have to do with all kinds of various things. They could be mismodeled chromatic errors from the interstellar medium. They could be intrinsic spin noise of the pulsar, or they could be a gravitational wave. So this is exactly how we model the gravitational wave background across all the pulsars. But of course, there we're looking for correlations across all the pulsars. So there's this additional term that sort of mops up anything that might be along one line of sight for a given pulsar. And in addition to those noise analyses, we also use something to look at the variations in the dispersion measure, because of course the interstellar medium is like big, giant galactic scale clouds that move in front of our pulsars. And so that variation needs to be taken into account. We use DMX, which is this piecewise constant variation in the DM. In the plot below, that's shown by these X's. And I'm not showing the error bars here, but the X's basically are at each epoch. Usually there's at least 2 measurements with 2 different receivers to be able to measure this dispersion measure variation fairly accurately. And this is supposed to soak up any of the variations in the dispersion measure, which is dependent on 1 over radio frequency squared. It also soaks up time varied scattering, which has other dependencies, maybe 1 over radio frequency to the 4th or 1 over radio frequency to the 4.4. And there's some interesting new results in Brent Shapiro-Albert's paper using the pulsar signal simulator to show that, in fact, some of these time varied scattering can get absorbed there as well. So we want to look at these noise models and see if we can make them better. And there's a lot of motivations for this. One of which is that sometimes DMX is not the best chromatic model, specifically when we have really spiky behavior. Something like the dip, the ISM dip in 1713, for instance, is a really good use of this. Also, DMX takes a lot of parameters, and we actually lose a lot of power through the transmission function in the pulsar. So when we're doing the timing model fitting, we add often 150 parameters. And so if we could make that a little bit smaller, maybe we can help in a Bayesian sense, at least modeling this, getting the Occam penalty down. So there's a few different motivations for this. And I'll show you the results, which I think are motivation enough in some sense. So we use Enterprise, our standard analysis code. It allows us to try a bunch of different noise models. We can model various radio frequency dependent effects. So the DM is 1 over frequency squared, and we can also test for higher order terms, and we can test for the most preferred model in a Bayesian sense through this hypermodel framework that we use. And I'm just going to jump in with the results here. And we can go into the details. If you are interested in working on this, or at some other point, please ask me about the details of how we do this and the various different models that we're using. But I think the proof is in the pudding. And so I just wanted to show 2 example pulsars. So for each pulsar, we work through various models and use a set of various metrics to try and figure out what the best model is. Part of this is Bayesian parsimony, and we just say, okay, here's a set of models, and we do an analysis, and where does the analysis spend the most time? That's the preferred model. And moving from model to model, we have to look at a lot of the output to try and understand things. When we take out DMX, we often get higher E-cores, which is the correlated high-frequency noise that we see. It's correlated across frequencies within an epoch, but not epoch to epoch. And so here I'm showing E-cores for these 2 pulsars and their red noise models. And so the bullet points tell us a little bit about what model is preferred, and these are sort of works in progress for these 2 pulsars. But the DM kernel, so the Gaussian process we're using for 1600 minus 3053 is a squared exponential, and there is a radio frequency dependent Gaussian. That's a radio frequency dependent Gaussian process, and there, on top of this squared exponential, there's also a piece, so that tells us something about the time correlations. There's also a frequency correlation part that's folded into this. And this is meant to emulate frequency-dependent DM. It turns out both of these pulsars prefer this model. So it's not just your straight dispersion measure model, but also it's taking into account that there may be differences in DMs at different frequencies, effectively different DMs at different frequencies. And in fact, both of these pulsars also prefer having a chromatic term. By chromatic, I mean a higher order term here, 1 over radio frequency to the 4th. We're still working on testing, so this could be radio frequency to the 4.4. We'll do that test as well to see. The only difference really is that one wants a squared exponential and one wants, in addition to that squared exponential, a little bit of periodicity in this dispersion measure model. So again, we could talk about those details later, but I think I want to really focus on the output here, which is that the E-core in both of these pulsars is decreased, sometimes dramatically. So for instance, if I look at the top left plot of this leftmost plot for 1600, the GASP log 10 E-core, there's a fairly significant detection, although maybe not super significant, to this orange posterior, which is really just an upper limit on the E-core. So really no measurement at all. And in fact, the Guppy one is even better, very significant detection of E-core down to again, an upper limit, so no significant detection. And in both cases here, we also have a huge change in the red noise. So in 1600, you have something that has a spectral index that's very, very low, near 0, which a spectral index of 0 basically means that there's some sort of unmodeled white noise, maybe mismodeled chromatic noise. And I say that because putting in these chromatic models turns out that the red noise effectively goes away. So you have something with a pretty significant amplitude and a very flat spectral index goes to no real detection of a spectral index and an upper limit on the amplitude. With 1744 for the red noise, instead, you actually have a motion of the spectral index from somewhere around 2, which would be unmodeled ISM noise, to something much steeper. And you can see that there's this shoulder here in the old analysis. So there's some sort of ISM noise or some noise at least with the spectral index near 2, and then something else creeping in. And we basically effectively get rid of this higher amplitude, lower spectral index part and only see something with this steeper spectral index. This is pretty interesting. And so one way to sort of see where this is going is just to look at the sensitivity curves that are drawn using these noise parameters. And here I've included the red noise parameters, and that can be a trap a little bit just because you don't know sometimes some of the red noise might actually be the gravitational wave background. But when it's very flat, like in the case of 1600, it effectively just adds white noise across the band. And so the dashed orange lines are the standard noise modeling. The blue is the advanced noise modeling. So you see that overall 1600 is better. The sensitivity curve is moved just a little bit further down. It's more sensitive. And this is really great. This is important for both gravitational wave background detections and detections at higher frequencies that we might want for single sources. 1744 is a little bit more complicated. It's interesting, again, for all of the high frequency part of the sensitivity curve, we have better sensitivity in the advanced noise modeling. But at low sensitivity, you see something different here. What's happening that's really interesting with 1744 is that, so the orange dashed line is the old, most significant red noise. So again, the max likelihood values for the gamma and the red noise are listed below. It's fairly shallow and pretty significant amplitude. And then when it shifts, the blue line, actually, look at the gamma there, it's surprisingly, or coincidentally rather, very close to the gravitational wave background spectral index that you would anticipate. The amplitude is higher than what we're saying we detect, but across all of the pulsars you have variations. And so even though this sensitivity looks like it's worse here, it appears, it's because again I'm adding in this red noise, that seems to be possibly the red noise from the gravitational wave background. And so that's really interesting to see here. So you're actually sort of peeling away noise and getting more significant detections in this particular pulsar. So that's it. That's just two examples of what you can do with this and what the end results are. If you're interested, there's a GitHub with tons of information on it. You can pull that. There's notebooks to start looking at and tutorials. If you are interested in joining us and adopting a pulsar, just send me an email and we can figure out what the best pulsar is for you, depending on what kind of resources you have and your interests. There's lots that we're going to be doing in this vein coming soon. We're talking about folding in nonlinear timing, which is what Andrew Kaiser has been working on into this process. As I said, the 11-year advanced noise modeling methods papers in the works right now with Joe Simon. And then we really want to try and tease out some of the astrophysics of these chromatic models and what that tells us about the interstellar medium for these particular lines of sight. And that's work that Megan Jones and Brent Shapiro-Albert, I've been talking with them. We've been talking with them to try and get them on board with some of that. So that's it. Please let me know if you have any questions in the talk channel, and thank you very much.